our colleague, Dr. Natasha Stanovic, to announce something normal lecture and give us the introduction for the presenter.
Thank you. Dear ladies and gentlemen, dear colleagues, Professor Giovanni Barla has been invited to deliver a lecture in a series of non-violent lectures with Croatian Geotechnical Society organized in honor of Professor Erwin Neuweiler. On this slide, we can see some projects and publications of Professor Neuweiler. And on these previous non-violent lectures from 2000 to present. Dear colleagues, distinguished professors, dear friends, ladies and gentlemen, allow me to introduce today's lecturer, Professor Giovanni Barla. Giovanni Barla, former professor of rock mechanics at Politecnico di Torino, has been head of the Department of Structural and Geotechnical Engineering and Vice President of the School of Engineering. He has been instructor and associate professor at Columbia University, New York, where he obtained his PhD degree defending a thesis of the analytical and numerical analysis of stress distribution around underground installations. Professor Giovanni Barla is editor of the Rock Mechanics and Rock Engineering Journal. He has been president of the Italian Geotechnical Association and Vice President for Europe of ISRM. He received the ISRM Fellow Award, the award for outstanding contributions from International Association for Computer Methods and Advances in Geomechanics, and the Emeritus Membership of Italian Geotechnical Association. He is honorary professor of Chongqing and Tianjin University and a member of elected of the Torino Academy of Science. The research interests of Professor Giovanni Barla span over a variety of topics in the fields of rock mechanics, tunnel engineering, rock slopes, dam engineering, and numerical methods in geomechanics. He is author and co-author of more than 300 papers, and also an active international consultant, providing valuable hints for new research topics. He acted in many rock engineering projects, including rock slopes, deep-seated rock slides, dam foundations, conventional and mechanized tunnel excavations, and mining engineering as designer, geotechnical consultant, or responsible of the numerical studies. Professor Barla is presently involved in a number of underground projects in Italy and abroad. He is contributing at the design stage of and during construction of the Alpine base tunnels and tunnels being excavated in difficult ground conditions. He is also devoted to the development of civil protection strategies for roadslide hazard assessment, methods for real-time monitoring and early warning, with reference to natural slopes in populated areas. Thank you, Professor Barla.
Thank you. Thank you, very kind. I really appreciate your kind word. Thanks a lot. It's a pleasure to be here, and it is an honor to give this lecture. I really hope to be able to meet your expectations. And I'd like to thank you really from my heart. Thanks a lot. I'm going to speak about novel investigation methods of rock slopes and tunnels. But the point is to be able to use these new methods in order to provide reliable realistic modeling in engineering applications. This is what I'm trying to do with this lecture. I will give you first a brief introduction about the two methods that I'll be using. Mostly I'll be speaking about terrestrial laser scanning and let's say advanced photogrammetric methods. And I think it is important to show you how this method can be used, as I said, in modeling, in realistic modeling. Therefore, I'll be speaking first through a case example by using 3D mapping with terrestrial laser scanning, how modeling can be done in order to understand problems, in order to understand instabilities. I will move then to the photogrammetric method, and again to show you how this method can be used. Of course, always by keeping in mind that in order to be able to do an appropriate mapping, you also need to be at the site. You need to be mapping, I would say, in a conventional manner. One method is, of course, used, and is going to help the other one. Then I have chosen a case history to show to you, with a case history, how these techniques can be used, always related to modeling. And of course, I'm using numerical modeling. And then I will just give you some concluding remarks, and I hope some questions. What we do generally in rock mechanics and rock engineering, of course, at the design stage and during construction, our point is to be able to describe and characterize, we say, the rock mass, I would say, in the most comprehensive way possible. And of course, a very important component of this process is mapping, and we do map rock exposures, rock mass exposures. You know, just to make things simple, we generally say that we need the orientation, we need, of course, dip direction, we need the dip, we need the spacing, we need the persistence, we need the roughness, the aperture, the wall strength, filling, seepage, number of joint sets, block size. I'm just using the ISRF suggested methods that, of course, elaborated a little bit, I would say. In general, what we do, we operate by using the scale line method, one dimension, and we use, let's say, the window method, two dimension. Of course, if I'm referring to, let's say, you know, a tunnel, or if I am referring to a slope, this is a nice looking picture, it's not very clear, of an exploratory edit that is being excavated under the Alps along the Lyon-Turin tunnel, which is going to be a 57.5 kilometer long tunnel under the Alps between Italy and France. And you see, of course, that we have quite a complex conditions. We have a fault, but if we were able to look carefully at the picture, you would see 5 different five different, let's say, conditions, giving you a very highly heterogeneous and anisotropic rock mass. Of course, you need to be at the face, and you need to be able to do mapping of this rock mass exposure. This is the same for a granite in the Lamma Island in Hong Kong. I go back a few years ago when I was quite young, and at that time we were working in Hong Kong, in Lamma Island, for let's say, analyzing the stability with very high slope. People there were creating space for what today is the Lamma Island power station, which is providing energy for Hong Kong. I go back to the 1979. But at that time, this is exactly what we were doing. We needed to characterize the rock mass, and all of this at that time was done by scan line, by line mapping, by window method, and of course by studying the rock mass exposures. And of course, let me just summarize. Of course, we are using surveys of the rock mass exposures. This is a nice looking picture of quite many years ago. At that time, I was doing mapping myself. Of course, I was much younger than I look today. And this is a granite, is a granite in the Sardinia Island. And we were mapping there just by using conventional techniques. This, of course, was done at this time on the surface, but it was also done on the ground. And we were using this usual methods, which are well documented, and of course, they are very well written guidelines, rules that you need to follow. Of course, I'm not speaking only of surveys of rock mass exposures, but of course, we are using borrow logging of drill cores. We can do this, and we have been using this quite well for many years. We do it, of course, by the help of PPV camera, borrow periscope, and of course, all of this allows us to identify the rock mass, the rock discontinuities at a small scale. And of course, we can measure very nicely also by these methods. We can measure the orientation, the depth, the width, the aperture of any planar discontinuity which is intersecting the borrow. This is, of course, is what we have been doing for quite many years and quite successfully. Just let me show you an example which I think, I hope it looks quite interesting. We are in Genova. There is Genova in Italy, and we are at the design stage of very important tunnels. These tunnels are very important. I'm sure that all of you are aware of what happened in Genova in Italy, the Morandi, let's say bridge that collapsed. And of course, these tunnels are going to provide in time new highway in order to be able to, in one way, to help significantly the highways and the communications in Italy in that area. Over there, we are dealing with the self-granite and more metamorphic rock, which is quite complex. You can see this is a rock mass exposures, and what you do there, of course, you go, you do line mapping, you do window survey, window mapping, and of course you are able to study extremely well the different characteristics of this highly disturbed anisotropic heterogeneous rock mass. And this you generally do by using conventional mapping. But of course, my idea now is to show you how this, let's say, conventional methods can be, let's say, in some way assisted by using, I'm saying, forgive me, new technologies. I'm saying on one side, the use of laser scanning, and the other side I'm saying the photogrammetric method. These are new technologies that have been developed and that, of course, are assisting us very nicely in this type of work. You can see here, this looks like, a very nice looking photograph. In reality, is what we call a point cloud. Millions of points which are giving you the real geometry of the face, of the tunnel face. This is a rock blast tunnel face. And you can see, I have chosen, this picture. You can see that you have two steel sets being placed. But you see that due to blasting, you have quite a significance, I would say quite a disturbance type of geometry. So much that in this area, the distance between the rock, between the tunnel profile and the steel sets, okay? Don't forget that the steel sets are placed and then you're going to place a shotcrete, okay? But you can see here that there is a distance between the profile and the steel sets. It means a geometry that is not what you would like to have. And of course, by using this type of method, you are able to see very nicely the geometry. I mean, all the geometrical features of your rock mass. And you are able to measure it very nicely. This is the tunnel again in Italy. We are near to the Mount Rouse tunnel. Mountain. We are up to 2,800 meter elevation with this tunnel. The geological conditions are very complex. Therefore, you are using also a pilot tunnel. Huh? And if I go on the other side, it's again a rock blast tunnel face, and I'll be showing this to you as a case example. You can see here that there has been a detachment from the roof of a rock volume which was detached, and you can see that the three images giving you by different colors the different discontinuities which are present in the rock mass. And what is important is that terrestrial laser scanning and photogrammetry can be helped also by using thermography. I'm going to show you an example in a little while. Let me just summarize and say what is terrestrial laser scanning. I'm looking to the future and I say, okay, let's use this new technology. We are going to obtain high resolution model of the rock mass surface. Our point is to investigate the rock mass surface in detail. They have different technology to do it, which are described in the lecture. What I'm using is the pool-based scanner. We are speaking of the time of a flight TOF scanner. And very simply, of course, I realize it. We are saying that the object is the distance between the scanner and the object is measured, and you calculate the round trip of the round trip time that the laser scanner pulse takes to reach the object and then to come back. On this basis, you come up with, of course, by using reliable and advanced software, you are able to obtain what I'm calling the point cloud. And you can see here, this is a point cloud which has been colored by optical images. You know, it looks a nice looking photograph, isn't it? And if I go on the other side, I can see that I've been using the thermography of the same face. You know, if I go in this tunnel, there's a pilot tunnel. There is air flowing, and there is a difference in temperature, which I can see with the color. This is extremely important, because I see it better here than over there, but you will be able to see it in the book quite nicely. You can see that the point cloud, by using infrared thermomap, allows you to see all the structures, all the discontinuities in a very nicely and well-defined geometrical manner.